We are going to dedicate today's class meeting to just working some examples, which it would be best if you guys could see. So let me turn the screen on. As I was mentioning to the people here in the classroom, I have posted homework sets 14, 15, and 16 regarding three-phase circuit analysis and three-phase power analysis, as well as your take-home portion of exam 4 already. I believe I set all of them to be due for next Friday, May the 20th at 5 p.m. But I will happily accept things all the way throughout the weekend since your grades aren't technically due until Tuesday anyway. Goodness gracious. All right. So if you've looked at the homework problems, you may have noticed that there are no circuit diagrams whatsoever. Everything is effectively expressed as a word problem. So the example problems that I'm going to work are of a similar type. So for this first example, let's say that we have a positive phase sequence balanced three-phased Y-connected source supplies power to a balanced Y-connected load. The magnitude of the line voltages is 208 volts RMS. And we are asked if the load impedance per phase is ZY is equal to 36 plus J12 ohms. Determine the line currents if theta, or actually, let me do this better. The angle of VAN is equal to 0 degrees. So once you get comfortable with working these type of problems, you probably actually don't even need to draw the circuit. Okay, but while we are familiarizing ourselves, we're going to go ahead and do just that. Okay, so we're told we have a balanced three-phase Y-connected source. So I'm going to draw my source over here on the left-hand side. So here's VAN. VBN. And VCN. I could also include a neutral conductor, but typically I don't worry about it because it doesn't actually really do a whole heck of a lot. So it's just drawing stuff that isn't particularly of use. On the right-hand side over here, I'm going to draw my Y-connected load. I'm going to have my 3 instances of ZY in a Y configuration. like so. Let's label our terminals A, B, C, capital A, capital B, and capital C. And in this particular problem, there is no mention whatsoever of any potential impedance for our transmission line system. So we are just going to assume that it's a short circuit connecting our source to our load. The information that we're given is that the magnitude of our line voltages is 208 volts RMS. So I'm going to say that the magnitude of VAB is 208 volts RMS, where VAB is representative of a line voltage, right? Because it's the voltage measured between our transmission line terminals. Our load impedance per phase, ZY, is 30 plus J12. And we are told that the angle of voltage VAN is 0 degrees. Excuse me. So these are the three things that are given to us. We are asked to determine our line currents. Our line currents are IAA, IBB, and ICC for this system. All right. So how we are going to approach this problem is using the single phase equivalent circuit model that we developed kind of in the middle of Wednesday's lecture. Okay. So for our single phase equivalent circuit model, just to be clear here, this is our lowercase n and this is our uppercase n terminals. We are going to have something that looks like this. So here is VAN. Capital A, here's uppercase A, uppercase N, lowercase n. Here's our impedance ZY. Our neutral conductor we treat as a short circuit, regardless of what it actually is. And then between lowercase a and uppercase a, we would have any transmission line impedance that we have, which in this case is simply a short circuit. And our quantity of interest is our line current, the current flowing from transmission line lowercase a to transmission line terminal uppercase a. So it stands to reason then that we can easily see our line current IAA using our single phase equivalent circuit is just going to be our voltage VAN over ZY. So my question to you guys is, how do we figure out what VAN is? Because we don't know what that voltage is. So effectively, that's correct, right? We don't necessarily have to treat it as if it were a delta connected source, but we do have a transformation that gets us from line voltages back to phase voltages, right? So what was that transformation coefficient? What did we multiply by? So if we wanted to go from phase voltages to line voltages for a Y connected source, what did we do? No. 120 would be to go from the A phase to the B phase, or the B phase to the C phase, etc. So if we want to go from our phase voltages to the line voltages for a Y connected source, what do? That's correct. So to go from VAN to VAB is multiplying by the square root of 3 angle 30 degrees. We're trying to go the other direction here, right? And we're really only given the magnitude of our line voltages, which means we can really only determine the magnitude of our phase voltages from that information, right? So how am I going to convert? How do I figure out what the magnitude of VAN is? Exactly right. So this should be 120.089 volts RMS. We are told very explicitly that our phase angle is 0. And so from this, our line current, IAA, is 120.089 angle 0 degrees volts RMS divided by our Y impedance of 36 plus J12 ohms, excuse me, gives us a line current of 3.165 angle negative 18.435 degrees amps RMS. Excuse me. I don't know. I got something caught in the back of my throat. So let's start. Does this methodology make sense? Right. Our analysis, our circuit analysis portion is always going to be one of the easiest things to do because we just have a simple single loop circuit, at least when we only have one load connected anyway. To determine the magnitude of our phase voltages, we had to remember what that transformation that we developed was. It allowed us to go from phase voltages to line voltages, or as Bradley suggested, it's effectively the exact same thing as going from a Y connected source to a delta connected source, vice versa. Since we were only provided with the magnitude of our line voltages, we could only determine the magnitude of our phase voltages. And then we had to use the fact that the angle for VAN was given. So this is our line current, IAA. How do we get IBB and ICC? This is what Connor suggested earlier. We rotate by negative 120 degrees. To get IBB, we rotate a further negative 120 degrees to get ICC. So without doing any extra analysis whatsoever, we can say that IBB is 3.165 angle negative 138.435 degrees amps RMS, and ICC is 3.165 angle negative 258.435 degrees amps RMS. Now, the angle for ICC is more negative than negative 180 degrees. So we could call this effectively positive, whatever 360 minus this is, and it would be the exact same result. I don't have any particular preference as the way that you choose to express them. But how I do it is always literally just subtracting 120 and then subtracting a further 120. So that it's obvious that that's how we're doing those phase shifts. So this, in my opinion, was a fairly simple and straightforward problem. A nice introduction. Let's increase the level of difficulty a little bit with example number 2. So for example number 2, in a balanced 3-phase delta Y system, the source has a positive phase sequence. The line and load impedances per phase are ZW is equal to 0.1 plus J 0.1 ohms, and Y is equal to 10 plus J4 ohms. If the line voltages at the source are VAB is equal to 208 angle 0 degrees volts RMS, calculate the line voltages at the load. So as per usual, I'm going to draw this circuit to help us get a better understanding of what it is that we're looking for. Here's VAB. Here's VBC. Here's VCA. And here we have terminal A, B, and C. On my load side, I have a Y connected load. Here's ZY, ZY, ZY. Terminal capital A, capital B, and capital C. And then finally here, connecting my source to my load is my transmission line network. Consisting of 3 instances of ZW. The information that is provided to me is that VAB is equal to 208 angle 0 degrees volts RMS. ZW is equal to 0.1 plus J 0.1 ohms. And ZY is equal to 10 plus J4 ohms. And what we are asked to determine are our line voltages at the load. So that would be this voltage, VAB, this voltage, VBC, and this voltage, VCA. Well, that one's measured from transmission line C up to transmission line A. So, in order for us to apply our YY or single phase equivalent circuit, we have to convert our delta connected source into a Y connected source. Right? So our single phase equivalent circuit is going to look something like this. Here's VAN, here's A, here's N. Here's the Y, lowercase n, capital N. Here's the W. So, one thing that I want to mention here, the quantity that I am interested in, VAB, isn't actually going to show up on my single phase equivalent circuit at all, right? Instead, what I'm going to be able to solve for directly would be this phase voltage VAN. Let's scroll down a smidge here. But we can see, or at least I hope we can see, that by performing Kirchhoff's voltage law around this top right-hand loop, we will be able to determine VAB knowing VAN and VBN, where VBN is just VAN shifted by negative 120 degrees, right? So our methodology here is to observe that our line voltage VAB is nothing more than VAN minus VBN, which is the same thing as VAN multiplied by √3 angle 30 degrees. Our conversion from getting from phase quantities or phase voltages to line voltages also works on the load side of the system. It has to, if we have a balanced three-phase system. So this is what we're ultimately going to do to determine VAB. So how do we figure out what VAN is? Well, that's going to come from our single phase equivalent circuit. Right? So I would argue, looking at this circuit, that's a simple voltage division relationship. Right? So we could say that VAN with capitals, our phase voltage at the load, is VAN lowercase letters, so our source voltage multiplied by ZY over ZW plus ZY. Line voltage division around our simple single loop circuit. And then the last thing that we need to figure out then is how do we determine VAN? Our equivalent Y connected phase voltage. Exactly right. Convert VAB to VAN using our conversion factor. So VAN is simply going to be VAB divided by the square root of 3, angle 30 degrees, which comes out to be 120.089 with an angle of negative 30 degrees, RMS, just using the conversion factor that we developed on Wednesday. From here, our phase voltage at the load, VAN, is 120.089 angle negative 30 degrees volts RMS multiplied by 10 plus J4 ohms over 0.1 plus J0.1 ohms plus 10 plus J4 ohms, which I get to be 118.655 angle negative 30.293 degrees volts RMS. And then VAB, one of the quantities that we're looking for, simply VAN times root 3 angle 30 degrees, which comes out to be 205.517 with an angle of negative 0.293 degrees volts RMS. Let me scroll back up here real quick. So the single phase equivalent circuit method allowed us to use simple algebraic relationships, right? Whereas if we had not developed a means by which to transform from a delta connected source to a Y connected source, we would have had effectively a very large system to apply nodal analysis to, or a reasonably difficult system to apply mesh analysis to, right? So understanding how these balanced quantities relate to each other allows us to avoid having to set up a system of equations at all, right? Since we know that in a balanced three-phase system, all of our quantities are exactly 120 degrees out of phase with each other, it makes the analysis, and everything has the same magnitudes, makes the analysis fairly straightforward. So, since we have VAB, how do we get VBC? Exactly right. And VCA would be simply another shift by negative 120 degrees, giving us negative 240.293 degrees volts RMS. This is more in line with what I would call a moderately difficult three-phase analysis problem. And the first one was pretty easy. This one was of moderate difficulty because what we were looking for wasn't actually going to show up on our single phase equivalent circuit. Now let's make things more difficult. This is the what I would consider to be the highest level of difficulty of something that I might ask you to do. So example number 3. We have a balanced three-phase system. Let's see, in a balanced three-phase system, the ABC sequence or positive phase sequence source is Y connected with VAN equal to 120 angle 20 degrees volts RMS. The load consists of 2 balanced three-phase impedances connected in parallel. A Y connected load with ZY is equal to 8 plus J2 and a delta load with Z delta is equal to 12 plus J3. If the transmission line connecting the source to the load is ZW is equal to 0.1 plus J 0.08 ohms. Determine the line currents and phase currents in the source, excuse me, in the load. All right. So we have a Y connected source. Here's VAN. Here's VBN. Here's VCN. Terminals A, B, and C. All right, so now let's talk about how we're going to make this load connection make sense, okay? So there's a delta connected load. So that means that we should see an impedance connected between transmission line terminal A and transmission line terminal B, that is Z delta. We should see an impedance connected between transmission line terminal B and transmission line terminal C, that is Z delta. And we should see a connection between transmission line terminal C and transmission line terminal A, that is Z delta. So that's our delta connected load. And what I'm going to do is I'm going to put a point out here in the middle, and that's going to be my neutral connection. So that between B and neutral, I see ZY. Between A and neutral, I see ZY. And between C and neutral, I see ZY. So this is what a parallel connection of a delta load and a Y load will look like. I also have my transmission line impedances to concern myself with here. So just 3 instances of ZW. And I'm going to identify my known quantities. So VAN is equal to 120 angle 20 degrees. ZY was given as 8 plus J2. Z delta was given as 12 plus J3. And our transmission line impedance ZW is given as 0.1 plus J 0.08. The quantities that we are looking for are our line currents, IAA. We're obviously going to be looking for IBB and ICC as well, but I'm not going to bother keeping on writing those because we know that if we find IAA, we can just shift our way into getting those. We're going to be looking for our phase currents through our load. So that's going to be this quantity IAB, as well as this quantity IAN. All right. So let's think about things here real quick. What is going to keep us from using a single phase equivalent circuit here? Yeah, so the fact that there's a delta connected impedance is going to kind of mess things up, right? But we have a means by which to convert a delta connected impedance into a Y connected impedance. How do we do that? So for the impedances, there's no square root involved. To go from Y to delta, we multiply by multiply by 3. To go from delta to Y, we divide by a factor of 3. So our single phase equivalent circuit is going to look something like this. Here's our voltage VAN, our transmission line impedance ZW, capital A, capital N, and then we're going to have our normal impedance ZY, and then we're also going to have a second impedance connected in parallel. And I'm going to call this Z delta Y because it is the Y equivalent representation of our delta connected load, right? Where Z delta Y is simply Z delta over 3 or 4 plus J1 ohm. All right, so let's identify which of our quantities of interest are actually going to show up on our single phase equivalent circuit. All right. So our line current IAA is definitely going to be here. Our phase current IAN is definitely going to be here. But our phase current IAB is not, because there's no connection to our B terminal here, okay? So let's talk about how we're going to figure out what IAB is, because I believe by simply inspecting our single phase equivalent circuit here, we probably have a reasonably good idea of how we're going to figure out what that line current is and how we're going to figure out what that phase current through our Y connected load is. To determine IAB, we can approach this in one of two ways. They give us the exact same result. What I'm going to do is apply Kirchhoff's current law at this node here, right? So if I apply KCL effectively at transmission line terminal A, what I'm going to find is that I have a current of IAA flowing in, a current of IAB flowing out, a current of IAN flowing out, but I also need to take into account that I have this current ICA flowing in, right? I have to take into account all of the different paths into and out of that node. I could rearrange this relationship and find that IAB minus ICA is equal to IAA minus IAN, where these two quantities on the right-hand side, I haven't yet figured out what they are, but they're directly from my single phase equivalent circuit. And recognizing that ICA is the exact same thing as IAB, except shifted by negative 240 degrees. This tells me that IAB times 1 minus 1 angle negative 240 is equal to IAA minus IAN, or IAB is simply IAA minus IAN divided by 1 minus 1 angle negative 240 degrees. So does anything about that methodology not make sense? To me, that's the most straightforward way of determining IAB. And by straightforward, I mean it's relying on simple practical application of things we know how to do, KCL, all that kind of good stuff. Another potential thing that we could do it'll give us the same result either way. If we found this voltage VAN, that's a phase voltage. Well, we know how to convert a phase voltage into a line voltage. So if we know VAN, we could potentially figure out what VAB is. And then we could divide VAB by Z delta. And that would also give us IAB. We're going to get the exact same number whichever way we do it. But to me, that second method isn't as intuitively obvious because it relies on multiple transformations and things like that. So my preference is the KCL relationship that we've developed.
Will we be using unbalanced?
No. So for an unbalanced three-phase circuit, you would do mesh to this thing.
All right.
Dylan. Okay. So ICA should always be flowing from the first subscript, terminal C, to the second subscript, terminal A.
Why didn't we start it as high as
Okay, so the reason why I wrote it as ICA as opposed to IAC is because when we're looking at our quantities, we're always going to go AB, BC, CA, and cycle back around. So if I had done IAC here, it wouldn't be as immediately obvious as what the phase shift would be, because it would be a negative 240-degree phase shift, but then I'd also have to multiply by an extra factor of -1 in there.
It's just like when you're writing your
Exactly right. Yeah, you go AB to BC to CA and then cycle back through them over and over again. Same exact thing for this, the phase currents. We could have absolutely done it as AC leaving, but then it would, to me, would take extra effort to figure out what the actual phase angle is supposed to be relative to the A phase of the system. So yeah, bookkeeping wise, this makes it easier for my brain to interpret. So that's why I'm going to do it. All right. So we have the math in place to figure out how we're going to get effectively everything. Now let's go through it. So how am I going to figure out, let's start with our line current, IAA.
B lowercase a divided by the equivalent.
Yeah, that'll absolutely do it. Yeah, so just treat all of this impedance right here as a single impedance, and then VAN over that equivalent impedance should give us IAA. Absolutely reasonable way to approach that. That would look like 120 angle 20 degrees volts RMS divided by 0.1 plus J 0.08 plus 8 plus J2 times 4 plus J1 over 8 plus J2 plus 4 plus J1. And this should come out to be 41.875 with an angle of 4.897 degrees. Amps RMS. Right. And then obviously from here, we could get IBB and ICC, but I'm going to stop doing that for everything because it's the same way everything. All right, so knowing IAA, how can we figure out IAN? Current division, absolutely right. We know the amount of current that's entering into this parallel combination of impedances. So using current division, IAN is going to be IAA multiplied by 1 over ZY over 1 over ZY plus 1 over the delta Y which I get to be 13.958 angle 4.897 degrees amps RMS. And then once I know IAA and I know IAN, I'm ready to solve for my last unknown quantity, IAB. If my stylus will write. And if I plug in my numbers here, what I find is that IAB is 16.118 angle 34.897 degrees amps. There is example problem number 3. This configuration is literally pretty much the hardest thing I could do. The only thing I could potentially do to make this configuration be slightly more difficult would be to give you a delta connected source. The reason why I say that this is as hard as it could possibly be is because if we had another Y connected load in parallel with this system, we would just have, ZY1 in parallel with ZY2 here, here, and here. We could lump those parallel Y connected loads together and make it look like a single Y connected load. Similarly, if we had multiple delta connected loads, we could just lump them together and make them look like single delta connected loads. So it literally can't get harder than this circuit. Yes, sir.
So for IBA or IBC and ICA, would those just all be phase shifts of IAB?
Exactly right. Just like IBN and ICN will just be phase shifts of IAN, IBB and ICC will just be phase shifts of IAA. Absolutely correct. So once we know how it works on one phase of the transmission line or the source or the load, we know how it works on all 3 phases in a balanced system just by shifting our angle. Catherine, were you raising your hand?
Yeah.
So a phase current is a current that flows through a single phase of a source or load. So IAB is a phase current because it's flowing through this phase of the delta connected load. IAN is a phase current because it's flowing through this phase of the Y connected load. IAA is a line current because it's flowing through the transmission line. Rajan. Okay, so sure, very, very quick review of so let's say that we have a network containing, I'm just going to do this as resistances, but it works for impedances or whatever, right? So let's call this R1. Let's call this R2. Let's call this R sub n. And we know how much current I is flowing into that parallel combination of resistances. Okay. Because all of our resistors are in parallel, they will all share the same voltage. So I'm just going to call that V. And I'm going to designate the current flowing down through resistor R1 as I1, the current flowing down through resistor R2 as I2, and the current flowing down through resistor Rn as In. If we apply Kirchhoff's current law, we will find that I, the current flowing in, is equal to I1 plus I2 all the way out to I sub n, right? So this is just telling us that our total current I that's flowing into the network splits among all of the resistors that it sees in parallel. Okay. Well, we can express all of those currents, I1, 2 through n, in terms of that common voltage V. So that's going to be V over R1 plus V over R2 all the way out to V over R sub n, or V multiplied by 1 over R1 plus 1 over R2 all the way out to 1 over R sub n. So what I'm going to do now is I'm going to rearrange this expression slightly and solve for V. Okay. So V is simply I, our total current, divided by 1 over R1 plus 1 over R2 all the way out to 1 over Rn. Well, the current flowing through resistor R1, I1, is V divided by R1, which is going to look like I times 1 over R1 divided by 1 over R1 plus 1 over R2 all the way out to 1 over R sub n. I2 is going to be I multiplied by 1 over R2 over that same denominator. And so generically speaking, we can say that the current flowing through the kth resistor, whichever one that we are interested in, is equal to I, the total current, multiplied by the ratio 1 over R sub K divided by 1 over R1 plus 1 over R2 all the way out to 1 over Rn. So effectively what we have here is the total current multiplied by the reciprocal of the impedance we want over the sum of the reciprocals of all of the impedances in parallel. There is a different way to express this for only 2 impedances in parallel, but effectively it has to deal with like the one you don't want and stuff like that. And I find that to be very confusing. So I don't like doing that one. Yeah. Right. Yeah, well, it's because, well, never mind, I was gonna shit talk your teacher, but I'm not gonna do it. This is the way that it should be taught, in my opinion, because this is applicable for any number of resistances in parallel. The way that you were taught is only applicable for 2 resistances in parallel. So this is much, much better. Also, it makes more sense because the resistor you want is in the numerator, not the resistor you don't want. So just every way that you can slice it, in my very arrogant and hubris-filled opinion. Connor, you're laughing at me. This is the correct way to learn this.
Facts are facts.
Yeah.
Everywhere I go, had the other way. I was like, what the heck is this?
Yeah, it only works if there's 2.
That's how it's so long.
Yes, this, in my opinion, it looks slightly more difficult, but conceptually it makes so much more sense because it's the reciprocal of the resistor you want divided by the reciprocal of all of the resistors in parallel. Whereas the other way, yeah, the other way would be if you only have 2, R1 and R2, I1, call this I, would be I times R2 over R1 plus R2. So the resistor you don't want is in the numerator, which to me doesn't make any damn sense. Like, I know mathematically why it makes sense, but from applying it, especially for you guys who haven't had the opportunity to do this over and over and over again, this way just seems wildly confusing to me. So I don't teach it in my Circuits 1 class. Right, for voltage division, that's exactly how it works out. The one you're looking at is the one in the numerator, and all of the things in series are the one in the denominator. In current division, with 2, very specifically, it works the opposite way. The one that you don't care about is in the numerator divided by, yeah, doesn't make any damn sense to me. Throw that garbage out and learn this.
I remember you talking about that in Circuits 1 and warning us about it, but I forgot about that. And then when I look back at my notes, I started doing it that way.
Yeah.
So
yeah.
Dr.
You can, whatever way you're comfortable with is fine, but if
I'm
you're,
comfortable with that.
yeah.
With interpreting this phased away between each node, the 120 degrees, it's, what is that describing? I know it's probably reaching a little bit outside.
No, it's not at all. We actually talked about it, but I think it was before you got here on that day.
Okay.
The reason why that occurs is because there's physically a 120 degree phase separation between the coils in the generator.
Oh, okay, interesting.
Yeah, so there's a physical, so if our stator is a circle, there is a physical 120 degree separation between the coils, between the A phase coil, the B phase coil, and the C phase coil, which in turn causes our voltages to lag by exactly 120 degrees as we go from phase to phase. And that lagging effectively propagates throughout the entirety of the system.
Is a magnet spinning?
Yes, that's exactly what it is.
that like inductive by any chance?
And that is exactly what it is. Yes. So it's working on Faraday's law of induction to where effectively, when the flux through the A phase is at its maximum, the voltage of the A phase is at its maximum. And then obviously the voltage of the B phase and the C phase are at lower values because they don't have the maximum amount of flux. And as it rotates, those magnetic fluxes change, which causes the voltages to change as a function of time. And you get three sinusoids superimposed on top of each other, all delayed by exactly 120 degrees of phase separation. Yeah.
A little